on this. Okay, somebody talk to me.
Hello.
Okay, I can hear that just fine. All right. So either I had too many things or I need to reboot my computer, but it seems to be working now. Okay, we had, where is, Neil was on before. So I'll wait a minute or two and then we'll go ahead and pick up where we left off with talking about how to analyze a cozy NMR. Okay. So, good. All right, one more minute. Okay, so this is a little bit different than what we had before in the fact that it has a few more correlations. And so this is more realistic to what we'll see in a standard cozy NMR. And again, there are not that many peaks here, but it gives us exact correlation. We're not just looking at the spins, looking at each other. We're looking for things that quit. So when this video gets uploaded, it'll be uploaded as 2 videos to our YouTube channel because, or maybe I can splice them together. Anyway, so I've already, the other part just converted and so. All right, so what I'd like to do is I'd like to continue on with this cozy or restart this cozy thing. So when we look at our cozy here, we have our Proton Nmr here and our Proton Nmr here. Notice they're exactly the same, okay? So it's not about that, it's about the things that are we can see within 3 bonds of each other. And so that's what we're looking for here. So the first thing we do when we're analyzing our cozy NMR is we draw our line through the middle here, okay? When we draw our line through the middle here, all it's telling us is this peak is directly related to that peak there. And so that's just telling us that yes, our cozy is lined up correctly and we do have the peaks we think we have. Okay, now that we've done that, now we're going to start looking at things that are off angle peak. So the first thing I want to do is I want to analyze this. I need to do some bookkeeping. I need to call this A, B, C, D, and E. So we just have to identify them as different things so that we can keep track of what's close to what. And then we have to use that same labeling system on the other axis. So this is A, B, C, D, and E, okay? Because they're exactly the same proton spectrum, they're just on 2 different axes, we can do this, okay? So that makes this peak technically our AA peak, meaning that that is our just A peak. So we don't have to identify those. Okay. So the first thing we'll see is this small little peak here. And sometimes we get these spurious little peaks here, but it might be real. So we're going to identify it because it's lined up with A on this axis and B on that axis right here. That turns us into an AB peak. And so that means A and B are somehow related within 3 bonds. Okay. So our diagonal peak here, and our first peak is our AB bond here. Okay. It's not very strong, but we're going to mark it anyway. Okay. The next thing we see here is that there is an AC bond, a nice big one. And notice how there's little spikes around the outside of that. Sometimes you'll see those. Those are sometimes overtones or like a split. So those will be like spinning sidebands or something you'll occasionally see, and they'll show up here, but they might not be individual peaks themselves. So that is kind of one of the little weird things about these 2D experiments. Okay, and I want to show you those peaks that were not there. Those were added. Okay, so the next thing we see here is we have a BE peak and a BD peak. Okay, so the B is from this side here, and notice that D and E are from here. So by correlating them, that means we have a BE peak and a BD peak as well. Okay, and those are pretty decent, which means that B is probably next to this E and D somehow. Okay, And then if we look at that, the last peak we have here is down here, down here. And this is our DE peak because we follow the one from the top down. It's an E, one over from here, it's a D. So that's our DE peak. Now notice we can find all these exact same peaks on the lower right side of the spectrum that the upper left has, but that's why we only need to analyze one of them. Okay, so these are our connections that we have. We know that B and E are within 3 bonds of each other and their hydrogens. We know that B and E and B and D are somehow close and related. And we have an AC. So we have that is close to that. And then we have maybe a BA here. But it looks like B is has a stronger signal with the E and the D than on this peak right here. So that's why I say this might be an aberration. And we might just have this AC connection. Okay. So now let's look at the signal. Let's look at the structure and try to identify where everything is just by shift. Okay. So if we're looking at this by shift, we're expecting to see this one and this one have to be the E and the D because those are the vinyl groups right here. And I mean, the vinyl protons. And it looks like E is probably this one because of shift. It's closest to the carbonyl. And so this would be D here. Okay. So the next thing we would identify is that I think that based on where the position is, it looks like this C and A are the ethyl group here. Just by shifts, that's where we would identify them from. And that our B would be this peak here, okay? So that being said, I think this small peak here, this AB peak is actually just an overtone of some sort and not really a true peak. So we're gonna look at the analysis of the rest of them, okay? All right, so if we look at this, what do we see, okay? We see that A and C are directly correlated and that there's no other connection between C is connected to no other carbon with hydrogens on it. A is connected to no other carbons with hydrogens on it. So that supports our premise that our group here is our A and our C. Right here, because those are the only 2 types of hydrogens that interact with each other. Okay, now let's go to the B and the E and D are related to each other. And that would be the fact that these are within 3 bonds of each other here. And then we have a BD interaction, which is here. And then a BE interaction, which is here, okay? Notice that this BE action looks like it's actually 4 bonds away right here, but we're seeing it in this correlation possibly because of the double bond or the through space interaction. Okay, so the D and the E are the only ones that are actually connected directly to each other, and then the B is somehow related to the D and the E through direct bonding. Okay. Okay. Do you see how we do the correlation where we only look at what is connected to what? And then by the strongest signals, especially these very strong signals like this, we have a direct 3-bond correlation. In this one, it looks like we have a possible 4-bond correlation, but we have it through a double bond. All right. Questions?
Can you hear me?
Yeah.
So you are saying that we have to follow the strong.
We have to follow the what?
The strong ones instead of the weak ones.
With this old example, yeah, there's actually a phase associated with it. So some are up and some are down because of where you are in the sign. And so these spurious peaks have actually been are actually more likely to be removed in modern machines than not. So we might not see them on other future ones, but this is an old example. So I think that we just have a phase issue in this particular example. But overall, we should see a direct correlation between that 3-bond interaction. Okay. So we'll do other examples, especially with our activity that we're going to do on Thursday. I'll have a couple newer versions of this that are cleaner. And then so we can actually see, some of them will actually be multicolored so you can actually see the phases. And so blue phases will be up and red phases will be down. And I'm going to talk about phases in just a little bit too. Okay, so we'll do another example of this, but this is the general concept of what we do. And it's basically the idea of, it's called bookkeeping by showing you exactly which things are connected to which things, and that helps us elucidate a structure. And as these structures get more and more complex, you'll start to eliminate certain connections because, oh, well, that's obviously more than 3 or 4 bonds away, so we don't have to worry about that. Okay. So that takes us to this cozy example. Okay, so in this cozy example, we're actually seeing the phase. Okay, okay, here we go. So in this cozy example, we have a total of 2 hydrogens, and because of their position in space, those geminal hydrogens actually aren't identical. And so there's a slight shift difference in there, okay? Now, because of that slight shift difference, these actually now also have different, the geminal thing has its own little coupling constant. Remember, our geminal coupling constants are rare and small. They're only between 1 and 5 hertz. But what we can see is once we do our off axis, so we have our, these are the peaks themselves, we see that this hydrogen is related to this hydrogen, and because they have different shifts, they are not equal. So the top left side of the graph, your typical NMR spectrum is correct. Yeah, so you would either have one at the top and it can be at either side. You usually have it at the top and one of the sides. And they should correlate to a diagonal line showing you that peak A here is going to be peak A here, such that because they're on the lines. Okay. And they're typically done in the same way from 0 to 10 and from 0 to 10, so that we get that diagonal line. Okay. Did that answer your question? Yeah. Okay. So in this case here, what we see is that this geminal hydrogen is different than this geminal hydrogen by X amount of coupling constant, but then the coupling constant between them is actually measured by looking at this. Now, in this case here, notice there are 2 black dots and 2 red dots. Well, those dots indicate phase, okay? So that one, if you look at it, you know, we have these oscillating spectrum, and so the one of them is going to be the up phase and one of them is going to be the down phase. And so in most of these cases, we'll see up phase and down phase to be across each other, but those, all 4 of those will actually be combined to make the signal that we see. Okay. Now, if we do a more complex structure like this, and so in this case right here, we have this hydrogen is unique and is labeled as our X hydrogen here. We have this hydrogen and this hydrogen that are, because of their spatial interaction, are not identical, and therefore they have their own shift right here. Okay. So, and in this particular case, we see that these 2 are looking at a geminal, a 2-bond distance here. And we can see that they have one shift, one coupling constant is associated with them being geminal. And then one coupling constant is associated with them having different shifts. And so when we look at that, we actually can see that as one shift is in one direction and the second coupling constant is in the other direction. And so we end up with the difference between these 2 sets is our larger coupling constant, our shift coupling constant, and this is our geminal coupling constant right here. And so we can see these arise and fall. And again, we have a positive phase to this system and a negative phase to the system, but they all are integrated together to give us a peak, showing us that M is correlated to A by that system. Now, because you can do that, you can actually measure the coupling constants of that by looking at that distance here. So again, our active constant, which is the shift-based difference, is what our larger coupling constant is, right here. That's just because of the shifts are different. That gives rise to this, our active coupling constant. And then the idea that these are split by the other system is our smaller coupling constant here. One is here and one is there. So that we actually get all three coupling constants, the one from being different shifts, the one from being geminal, and the one from being associated 3 bonds away from our third proton. Okay, so we can actually get all those. Now, if we take all that information and add it together, we can actually see that, well, in this case here, we've actually added another proton here. So in here, we had a O deuterium on there, so we changed it. We'll actually see that third. We actually see a decrease in the number of paths in coupling constants because these now become identical. And we're only looking at the shift to the methyl group, this hydrogen here. So now that we've taken off that OH group, all three of these hydrogens are no longer different. Therefore, they are a single signal. And they're only split by this hydrogen. And these hydrogens here, I mean, this hydrogen here is unique and only splits those. So we end up with our 3 peaks, which is our N+1 for splitting of this right here. It gives us a total of 4 peaks here. And our N+1 for these 3 all being the same split by 1 gives us these 2 peaks for that. But now our coupling constants have condensed into showing all 4. Our 4 peaks for our quartet we get from just our standard 3 bond coupling constant, and our other standard 3 bond coupling constant. But then there's that through space, which is our active. I mean, active. So, but most of the time we don't have to do this because we now have computer controls that actually analyze this and pops it out an analysis with our coupling constants at each system. But we're still looking at the same thing where we have this peak is definitely within 3 bonds of this peak, showing us an intense signal. Okay, so let's apply that to this particular cozy right here. It's again a fairly simply cozy, but we'll do the same thing. Notice we have a proton NMR here and a proton NMR, here and here. And we're gonna label this A, B, and C, which makes this A, B, and C. And we're gonna draw our diagonal line, okay? So in this case here, we wanna see the connections between the different bonds. And the first thing we see is that B is not correlated with any other hydrogens in the system. That means it must be an isolated methylene. So it has to be a CH3 that's isolated by something. I'm gonna, because of the shift, I'm gonna say it's a carbonyl. Okay. So the other 2 peaks, we have an AC grouping right here. And if you blow it up here, you'll notice that there's 2 colors there. One's the up phase and one's the down phase, but they link all together to create a nice little connection here. And what we see here is that the A and the C are the only 2 in this spectrum that are within a 3 bond limit. So that's suggesting, and with the splitting here, that's suggesting we have a CH3, CH2 because of number 1, and they're right next to each other because of the shift and the correlation diagram. Okay. So obviously that's a very simple example, and as we move forward, we'll see that getting more and more complex. Okay, and so this is just a blow up of those first 2 peaks, showing us that if we show that, we can actually see we have our first active coupling constant, our active coupling constant, our inactive coupling constant. So there we go. All right, so questions about the basic analysis of COSY proton-proton NMR.
When you assigned peak B and you said that based on the shift, it was likely a carbonyl, what shift are you referring to?
When I assigned B, I said it was a methyl group because it was isolated. It's isolated because of the idea that it is, it's not split and it's not correlated to any other protons in our system. And I happen to know that this is 1.1, this is 2.5, and this is 3.1. So looking at the shift of the COSY NMR, just the regular 1D proton NMR, you'd see the shifts would correlate to something you'd expect. So what we probably have in this is the ethyl acetate. But it was just an example. I just wanted to show you the correlation on this, not necessarily the absolute shift. Okay?
Okay.
Okay, let's see. Okay. Oh, 12 o'clock. Okay. All right. So, oops. All right. So that is COSY. And that's the first of our cool experiments here. Most of the time we are looking at just that 3-bond interaction, and that's gives us a lot of information about this CH2 is attached to this CH2, but not this CH2. And that's where we get the most information from this. Okay, now the next thing I want to talk about is Headcore. And we actually have 2 different ways to do Headcore, what we call absolute value. And absolute value gives us basically, you know, we have ups and down phases and it kind of sums them together. But then we have phase sensitive Headcore. And so what we'll see here is just like, is the graph on the right in the zoom of the, that's just the AC coupling. Yes, it is. In phase sensitive, just like in a DFT experiment or a DEPT experiment, you actually can see CH2s versus CH3s versus CHs. So it's almost like a Headcore with a DFT added to it, okay? So, but it's harder to work up the phase sensitive Headcore. So absolute value Headcore is what I'm going to start with because it's easier to see what we have. And in Headcore, we're looking at what protons in our proton spectrum correlate to what carbons in our carbon spectrum. Okay. And just to give you an idea of what the phasing looks like in a 3-dimensional graph, it's because remember, when we're looking at our sinusoidal wave, we either catch it on the positive side of the phase or the negative side of the phase based on the time regime. Remember that DEPT experiment where we had the 3 different phases and how in one phase, all of them were positive. In one phase, 1 was negative and 2 were positive. This is the same thing where we get to see at different time regimes, we have different positive and negative additions to our spectrum. And if we were to graph it in 3 dimensions, we'd see these kind of spiked peaks here. But of course, and while they're pretty, they're very hard to graph. So most of the time what we see is we use this 2-dimensional plotting of it, where the positive phase is one color, typically blue. The negative phase is one color, typically red. And so when you overlap them, you get that kind of that 3D effect of understanding that you have the 2 different phases. Now, again, in the absolute, we kind of we take the absolute value of them. So all of them become positive and they kind of blend into single groups. Okay. So within Headcore, we have 2 different things. We have what we call quantum coherence and multiple bond coherence. So in quantum coherence, we are looking at just a direct hydrogen to carbon correlation, okay? So that it means that if you have a carbon NMR and a proton NMR, this proton shift in the NMR works with exactly this carbon and nothing else. So we end up with a 1-to-1 analysis of our system. However, you can also, by changing your time regime, you can actually see the 2-bond connection, which is, so if you had a hydrogen here connected to a carbon, connected to a hydrogen, to another carbon. This carbon would show up connected to this at a weaker signal than this one. So you have carbon number 1 has its primary signal. Carbon 2 now see through 2 bonds. And sometimes you can actually see through 3 and 4 bonds. So it's, again, it's still a carbon related to hydrogen, but in the QC, HMQC experiment, it's exactly that carbon. And in the BC experiment, you can do 2 to 4. Okay, so you can see greater, longer connections. Okay, so it makes it harder to analyze the multiple bond coherence, but you start with the QC first and get exactly, and then if there's still an ambiguity about connection, then you go to the multiple bond correlation, and then you can say, this H is 1 or 2 bonds over from this carbon, so now I know I can have to draw it in that specific correlation. So what do these look like and how do we analyze them? Okay, that's what we're gonna do next. But, so with the quantum correlation, multiple bond quantum correlation, we have a difficulty because you're looking at multiple signals, okay? With your standard Headcore, which tends to be the single bond correlation, we have fewer scans necessary, and it gives you 1 peak for each of the connections, okay? And typically all of the proton-proton couplings are removed from them so that it makes it easier to do, okay? And then there's a bunch of different ways you can vary this experiment, but generally Headcores we want to do with the absolute signal, so they're all up, so that you don't have to worry about whether it's in phase or out of phase to determine whether you have 3 hydrogens, 2 hydrogens, or 1 hydrogen on them. Okay, so the multiple bond correlation actually is really cool because now you get additional information about the different shifts that you have, although it is tends to be a little more sensitive so that you can actually see the connections as they evolve throughout the longer molecules. This works well if you have multiple double bonds or multiple connections and you're trying to figure out exactly where they are. Okay, so what does that look like? So if we look at the, I don't want to do the multiple bond first. Yeah, that's the multiple bond. Okay, so this is just our single bond carbon to hydrogen comparison. Okay, so the first thing we notice on this is, number 1, there's not a diagonal line through there, but we'll talk about that in a minute. And the other thing is, this is our proton NMR, and this is our carbon NMR on this side, okay? So what that means is, if we see a peak, that that carbon is attached to those protons, okay? So if we look at this, carbon number 9 is associated with hydrogen A, and it looks like there is maybe multiples hidden under here. So notice in this case here, if we were just trying to do that proton NMR, we would see, oh, well, there's a whole bunch of protons overlapping each other here, and I can't differentiate them. Well, it turns out those hydrogens are on 1, 2, 3, 4, 5 different carbons. So we have this whole peak, if we take this whole peak as A, right here, because we can't differentiate them just by proton NMR, right? We don't have baseline selectivity. We don't have a really good splitting pattern. And I bet if we looked at the integration, it would look very noisy. So we can't identify it just with the proton NMR. But we can say that we have carbon 9, carbon number 9 has A-type hydrogens, meaning that they are the lowest shift down, so they're the most hydrocarbon-like. But we also have carbon 10 and 7 are associated with this, let's call that A1 and A2. These are A2 and A2 peaks. And then this one right here looks like it's correlated with an A2 peak. This is correlated with an A2. And then this is actually the separated out. So this one right here is only on carbon number 2. Okay, so that means we have 1, 2, 3, 4, 5, 6 carbons that have this type of hydrogen in them, okay? And so their shifts are very similar, and so they should look fairly similar. Okay, now let's go to a couple of the easier ones right here. This one, right, these hydrogens here, I'm gonna call B, C, D, E, and F. Down here, actually, is that a, yeah. So, and I'll show you why. I skipped this one in a minute. So the hydrogens at B correlate to carbon number 5. So carbon number 5B, that's an exact identification that carbon 5 has these hydrogens on it. And so if you had an integration on there saying it was 1, 2, or 3 hydrogens, you would say, okay, these 2 hydrogens are on carbon number 5. And in this case, it's probably integrates to just 1 hydrogen. So this shifted hydrogen correlates to just carbon number 5. Okay, we move over to C. These C's are only related to, I don't know, it's either 3 or 7. So C is, I'm going to just call it 3, I guess. D is only on carbon number 6. F is only on carbon number 8. I'm sorry, E is only on carbon number 8. F is only on carbon number 1. F is only on carbon number 1. And wait a minute, there's a peak I skipped. There's a peak I skipped. And when we go down here, if we look all the way down here, there's no associated peak with it. What does that mean? It means that
with no hydrogen.
It's either an OH or
Oh,
an impurity. Okay, so because these hydrogens are more than 1 bond away from a carbon, we don't see them. So we have to think, all right, we either have an OH or an impurity, or that's our solid. In this particular case, we do have an OH. So that makes these hydrogens our OH hydrogens on here. Now, do you see how we have, especially when you have peaks like this here, that it correlates directly to carbon number 8 is associated with these hydrogens on E. Okay. So if we look at the structure, carbon number 8 has 1 hydrogen on it. And so we could probably, if we looked at the integration and we saw that this had 1 hydrogen on it, we would be very confident that we had that group there. And notice it's kind of split into a multiplet, so we don't see it. 9 and 10 have these methyl groups right here. So they're associated with this first peak here. Okay, so let's look at another one. The next up here is carbon number 10. So, carbon number 10 is this methyl peak here. And we see that those are also associated with these hydrogens here. So that means that this peak is actually split into 2 peaks and has these carbon number 9 and carbon number 10 are different in space. Notice one of them is closer to the OH and one of them is farther from the OH. And that gives rise to this split here. Okay. So, all right. So let's look back at our structure and see if our shifts start to make sense based on where our proton shifts are and where our carbon shifts are. So let's just start with the idea that 3, 7, 10 are all 3, 7, and 10 are all the same, in carbon shift. But we have 3 protons, we have 3 protons, and we have 2 protons here. So where does 3 7, and 10 all fall under this group, this A2 group. So A2 should integrate to 7 protons. Okay. 9 is mostly here, but it's looks like it has a little bit of splitting here. So this should integrate to 3 protons. Okay. Notice 4 right here is also in there. So 4 is another 2 protons inside this coupled link. So that means we need to add 2 more protons to the total integration under here. And then what else is there? This one. So 6 for 2 more protons. So we have 2, that's 3 protons, and 9 is there, so that's 3. We have 6 and 9, so there should be a total of 15 protons under here. We could not have identified what those 15 protons were based on the Proton Nmr. Okay, because those 15 protons are on 5 different carbons. Let me call it 6. 1, 2, 3, 4, 5, 6. Okay. Now, the ones that are starting to differentiate themselves are getting easier. This one right here is only correlated to bond number 2. So that means that single, let me do a different color here. This peak right here is only associated with carbon number 2, which means this right here has that 1 hydrogen here. And we have completely isolated it from the rest of the system, knowing that it's exactly that. Just like B here is only correlated with carbon number 5. So that's this one right here. This 1 proton is now uniquely identified. So we tell the difference between this 1 proton and that 1 proton in our ring system. Okay, could we do that by shift? Maybe. Is it easier to see in the Headcore? Probably. Okay, and to follow along again, these protons are only associated with number 7. And number 7 is, oh, right there is a separate one. That's 7, 3, 7, 2. Well, maybe that's 3. Yeah, maybe this is 3 then. So maybe this is these 2 protons here. I don't know, I'd have to get a ruler out and draw lines all the way across straight to make sure. It's either 3 or 7, one of those 2. D here is only associated with carbon number 6. So that turns, those are our D protons. F is only associated with carbon number 8. So that's this carbon number here. So those are our F protons. Our H proton is the one on the oxygen because it has no carbon correlation. And F is only on number 1, which happens to be the one on the oxygen here. Okay. iPads have a ruler tool. Really? On the...
Yeah, if you click the little marker button in the bottom corner.
Oh.
Yeah, and it'll help you draw a straight line.
Oh, that's so cool. Thank you. So yeah, it is associated with number 3. And that one is closer to number 7. And that one is closer to number 10. And both of these are associated with number 9. Okay. Oh, that is so cool. Thank you. So that's definitely 5. This is definitely 4. And 4 has splitting there and there. And then that's 6. And then we rotate. Ooh, cool. It even does 90 degrees. So that we can do that one there.
You can also use it to draw a line. And I'll do like a perfectly straight line.
This will?
Mm-hmm.
How do you tell it to draw a straight line? Or
I
you...
think you get to click the marker
Okay.
and then start drawing.
Oh, that's so cool. Oh, Wow, I'm on video saying this. Okay, all right, sorry. That is neat. I like that. So you can actually take these and draw. Oh, wow. I'm gonna have to redo this lecture. Look at that.
I have a question.
Yeah.
Why the single carbon is showing two signals, like carbon 4 and carbon 6?
Okay, so part of that could be that there's a big enough coupling constant that it's showing up in two places, which is why it's that way. So that part of the signal is like, let's say you have a big coupling constant of like maybe 10 or 12, that you're actually split into two peaks, but because we can't identify individual peaks here, we don't have peak to peak separation here. We could have a doublet of doublets laid on top of a triplet, laid on top of a quartet, and we just wouldn't be able to differentiate them in the proton. This happens a lot, especially in rings, because we're kind of fixed in space. And even though it's, quote, fixed in space and can flop right here, because we have that big isopropyl group, it's going to be stuck where that isopropyl is going to be probably at the equatorial position. And that's going to change where we see these two peaks in particular, because they're kind of locked in place because of the ring. So if this was a long chain alkane where we had all that free rotation, we would probably see a greater separation. Okay. So this is just that single bond correlation. It shows you just single bonds that carbon is attached to those hydrogens. Okay. Now, if we do the multiple bond correlation, what we start seeing is something that gets a little more complicated. Okay. So, and here we have to worry about intensity. Okay. So the ones that are more intense are the ones that are closest to single bond interactions. And then the next most intense are going to be those 3 bond interactions, the 2 bond interactions, the carbon going over 1. And then the least interaction are going to be them going over 4. So this would be like a 4 bond interaction. This would be a 2 bond interaction. This is a 1 bond interaction. Okay. So the intensity becomes important when we start looking at that system. So let's just take one example of this and try to figure out, let's see, let's do carbon number 3 here, because carbon number 3 has connections to 1 proton plus 2 protons. So let's do carbon number 3 here. And we're just going to draw a line there, making sure we have those. And let's see what's closest attached to that thing. So we have carbon number 3 is associated with this. This is, again, hydrogen F, and this is hydrogen E. So let's see, 3 is associated with, so F was the one that is on carbon number 1 right here. So there is a 1, 2, 3, the carbon-carbon bond, the carbon-carbon bond, and then the carbon-hydrogen bond. So that's 1, 2, 3 bonds over. So this is a 3 bond connection to carbon number 3. Okay, so E right here is this number 2. So it's a carbon over 1. So that's a 2 bond connection. And notice how it's more intense right here. And then the carbon that was attached to these hydrogens that are attached to 3, which are C, which is this 5 here. Notice it goes away. So this is where they were attached the first time. And because we have now diminished our 1 bond signal and are looking at our 2 and 3 bond signals, our 2 and 3 bond signals are the ones we see. So that's the advantage of our multi-bond correlation, or MBC, versus our quantum correlation, which is the direct 1 bond correlation. So the bonds away, the less intense the signal. The more bonds away, the less intense the signal, yes. Okay. And let's take another example from just this one right here. And let's look at, okay, so these are identified. So we've actually identified A, B, and C on these. They're numbered 1, 2, 3, 4. Okay, so the hydrogens here are the hydrogens on those carbons. Okay, so in this identification, they probably identified these hydrogens, this group of hydrogens, based on the quantum number. And notice 6 and 4 and 3 and 10 and 7 and 9 hydrogens are all overlapping each other. Okay. So now let's see if we can correlate that to, let's talk this bond right here. Okay. So that's one hydrogen there. And so we have this atom is going to give us a 2-bond correlation. This atom has a 2-bond correlation. This atom has a 2-bond correlation. This atom is going to have a 1, 2, 3 bond correlation, 3 bond correlation, 3 bond correlation, 3 bond correlation. So we should see a total of 6 things that are attached to that number 2 carbon, plus the initial signal itself. So let's take a look at that. And we're going to draw our line here to show where our 2 carbon is, right here. And then I'll make that go away. And then we're looking at our number 1 carbon is going to be a single bond. And we see number 1 is a 1-2 bond correlation. Number 8 is a 2 bond correlation. Number 3 is a 2 bond correlation. Where we have 9 is a 3 bond correlation. 10 is a 3 bond correlation. And 4 is a 3 bond correlation. That's this one right here. And 6 is a 3 bond correlation there. Okay. So all of those connections do appear on our multi-bond correlation spectrum. Okay. So if we looked at our single bond, some of those peaks wouldn't be there. If we look at our multi-bond, they are. So we know the connections are there. And by color coding them this way, we can actually see that, yes, the 2 bond connections, the 3 bond connections all exist. Are there 4 bond correlation here? So the 5. 5 would show up. I don't see much under there. What else would be? 5 is the only one, the correlation for the 5th, for the 4 would be this one right here, but we don't see that. Okay, questions?
So this spectrum, you can even use this thing only when you know the structure of the compound.
No.
If we don't know the structure of the compound, then.
Okay, I have the structure on so we can see where things are as we go through it. That is the thing I'll talk about next time. It's called the accounting method, where we try to figure out what's going what. And so by creating a little table of, oh, this is connected to this and this is connected to that, we'll be able to divine the structure with just these spectrum. So it's going to be harder to get the spectrum out instead of showing you where the peaks should be. So I've done it this way first. We're going to go the other way next. Okay?
And the other question is, when we are using the carbon spectrum, so we're only correlating the carbon-carbon ones. And when we are using the Proton Nmr, we will be correlating only the hydrogen and hydrogen.
So if we're doing the cozy proton or carbon NMR, then yes. It's just a direct carbon-to-carbon correlation. This is the Headcore, where we're showing where the combinations between the hydrogen and carbon are. Or did I answer that question? Was that what you're asking?
Like I'm about asking this spectrum that you are showing about the HOMO ones. So HOMO ones is for the similar atoms, carbon-carbon and hydrogen-hydrogen.
Oh.
So when we are using the proton one, we were just correlating the hydrogen-hydrogen.
Correct. And in the proton only, the proton cozy, That's only a 3-bond correlation on there. With the Headcore, the first type we do is a single bond correlation, carbon to hydrogen, and then this is the multi-bond. So this does the 2, 3, and 4 bonds out that we don't see in the other system. Okay, does that answer your question? Okay, good. Okay, so next time we're going to pick up on this, and we're going to do a little more. We're going to actually go with some of the other correlation kind of thing and showing you that it's much easier to do this with software, but we'll get to that as well. But we'll, and then I'll show you the accounting method for trying to discern the structure from the Headcore as well as. Usually we have a good idea just from analyzing the proton and the carbon spectrum. So we'll have like 1 or 2 or 3 choices based on just shift and position and integration. But then we have to use that to say it can be this one, it can't be this one, it can't be this one, okay? So rarely do you run to here to just get the first attempt at drawing your structure. You actually say, oh, it could be this, could be this, could be this. I don't have enough information with just the shift to prove one or the other. That's where the Headcore experiments help you decide which of those it can be, okay? All right, I'm a little over time, right? Yes, I'm sorry. A little over time, but we lost that a little bit. But hey, I can hear you speak, and that's great. We solved a problem at least. All right. All right, well, thank you very much. I'll post an additional set of slides, but we probably won't get to it next Thursday because of our activity. But we're going to go a little more into depth about these Headcore with 2-bond and multi-bond connections and the accounting system on how to do them. All right.
What we will have in activity?
Sorry, what?
What we will have in activity, like carbon NMR and through direction, both?
We can, that doesn't tell us as much information as the carbon, the hydrogen 3-bond correlation and COSY tells us a little bit more. But we do have another technique that's carbon-carbon technique that I'll introduce, okay?
So to prepare for the activity on Thursday, we should look over the COSY section.
Well, I'll give the pre-lecture on that and give you kind of an idea of what to look for. It'll be kind of based on this structure, or based on this Headcore, which structure is it going to be? Okay.
Okay.
So, all right, I'm going to stop recording and how